have a look at this topic called calculus. And I suppose my first question is, have you ever heard of this before, and what do you know about it?
I've heard of it, but I've never even looked at a paper on it. So pretty nice.
So, does it sound like anything that you've done, that word?
I know it has still to do with like graphs and with like X and Y, but I've never known any more than that.
Okay. Does it sound like calculating at all?
Yeah.
Okay, and the root word actually comes from that. So in Roman times, they used little round pebbles to help them do their calculating. Other cultures used abacuses and things like that. The Romans used little round pebbles, and they called those pebbles calculi. Now we've still got that word because we use it as in renal calculus. And renal calculus means kidney stones, which are little round pebbles in your kidneys that hurt like hell until you get rid of them. So it's got that meaning. But actually, the topic that we now call calculus sort of started about 1660s, 1680s, and there were two people who worked on it. And the whole idea was to think about how things changed, rates of change, which you've come across before. But it's a slightly different aspect to that. It's how things change over a really tiny interval of space or time. And in fact, Newton, who was one of the key fellows, was looking at how planets moved. And he knew that he could see a planet there one day and here another day, so its average speed is a rate of change, would be whatever. But he also knew that planets changed their speed as they went round their orbits, and he wanted to know what was the speed now. And that was his whole investigation. So it's a little bit like in your car, your speedometer tells you your speed now. Okay, so that's sort of where it's all come from. It's this idea about how things change over a tiny, tiny interval. Now I thought we'd start with what you actually do know. So we'll start with those ideas about rates of change. Okay, and here is a question that you've probably seen something pretty similar about lines, and supposedly it's probably a silly context. So we've got different costs for providing afternoon tea snack for so many people. Okay, and we've got different companies. So could you identify from these descriptions which of these fit which of the lines?
Yeah.
So which is which?
A is the green line.
So just write it on it. Yep, cool.
And then B is the blue line.
Cool.
And C is the red line. Because they start with the flat feet.
Cool. So could you write equations for those lines?
Yes.
Good.
Do you want?
Yeah. Cool. So, in those equations, which part of those equations describes the gradient or the rate?
This part.
Cool. Okay.
That's just the intercept.
Okay. So, if you think about all of them together, is there something that you can say about the gradient for these lines?
They're all like positive, I guess. They're all going
Good.
up.
Good. On this blue line,
Mhm.
whatever the gradient is here, is it the same up here?
Yes, stays the same.
So for each of them it stays the same.
Mhm.
Okay. So this is the part where calculus comes in. Calculus says we want to study the gradients. And for lines, gradients stay the same all the time. So if we were to draw a graph just of the gradients, this one here has got a gradient of,
0.
and it's 0 all the time. So if we were going to graph it, we would graph it at 0 all the time. Do you want to scribble a line in there? Cool. And the next one would have a gradient of, so the blue one would have a gradient of,
2.25.
cool,
So it would be
roughly there,
ish.
and it would be
Constant.
constant. So it's constant gradient, well done. And the other one is also a constant gradient, and it would be across there. Cool. Now, here comes the problem. It's awesome with straight lines. Gradients are the same, they stay the same. If you looked at a graph of a parabola,
Mm.
what could you think about gradient?
It changes. And it can be steeper and it gets sort of less and less as it goes out.
Cool. And is it always positive?
No. What? Yeah. But never. No, because it can be on the negative side, so no, it's not always positive.
So, if we looked at a different graph, go away. So it's a cubic graph of some description.
Mm-hmm.
What's happening with the gradient now?
It's changing like the whole time. Mm. But it looks like it will be the same there and there.
Okay. And probably here's one of your favourite graphs.
So
What's happening with its gradient?
it's constantly changing, but it becomes the same each time.
So calculus is actually the study of those gradients and what's happening. So if we look at a different series of graphs, where is it? Yeah. Okay. So what it was decided is, how do you quantify that gradient? We can see that it changes. How do you quantify it? And what was decided and mathematically worked out is that you can actually think of the gradient of the curve as being the gradient of the tangent at that particular place. And so I've got one tangent line in there, but I've also got this cute little slider. And so as we move across the graph, we can see that tangent changing. And so at the moment, the tangent would have a gradient that is,
Negative.
and then it's getting,
It's getting like less steep.
cool. And at this place here, it gets to,
Perfectly straight.
so its gradient value would be,
0.
and then it starts,
Become more positive.
and more
Steep.
steep. And we could change that graph to anything we liked. So if we went to a, let me see, 3x cubed